Lesson 5. Factor the following expressions completely. So x to the fourth minus 81. Hopefully you recognize this as the difference of perfect squares. That's something squared, that's x squared squared minus 9 squared. So that means that expression can be rewritten as x squared minus 9 times x squared plus 9. Again, it wants it factored completely, so we factored it once. Can we factor this expression anymore? Yes, we can, because x squared minus 9 is again the difference of perfect squares, x plus 3, x minus 3, and as we talked about in the lesson, we can't factor the sum of perfect squares. So x squared plus 9. So x to the fourth minus 81 is equivalent to x plus 3 times x minus 3 times x squared plus 9. They look different, but have the same value. X minus 1 squared minus 4. So we need to get used to looking for and making use of structure. If I had you factor y squared to minus 4, you would say that's y plus 2, y minus 2. But instead of a y, we have this chunk of x minus 1. So instead of a y, this is really something squared minus something squared. So that y is really x minus 1 plus 2 times x minus 1 minus 2. And then we, of course, can simplify that to be x plus 1 times x minus 3. If you multiplied that out, you'd be able to get a trinomial and factor it, but looking for and making use of that structure saves you a bunch of time by recognizing this as something squared minus something else squared. Factor the expressions completely. Y cubed minus 125. So y cubed is a perfect cubed. 125 is a perfect cube because it's 5 cubed. So we have y cubed minus 5 cubed. So we know from today that we can factor this as y minus 5 times the first term squared plus the product of those two, the y and the 5, plus the second term squared, 25. That's just using the difference of perfect cubes formula that we developed today in class. 27x cubed plus 1. Again, this is the sum of perfect cubes. That's 3 cubed, 3x cubed plus 1 cubed. So the sum of perfect cubes, I know that this expression is equivalent to 3x plus 1 times 3x squared. 3x squared is 9x squared minus the product of 3x and 1. 3x times 1 is 3x plus 1 squared, which is 1. Number 3, factor x to the 6th minus 1 completely. So there's actually two ways to go about this. There's two ways to go about this and say, hey, that's the difference of perfect squares. That's x cubed squared minus 1 squared. Or you can say that's x squared cubed minus 1. Either way is going to work, but it's going to be more beneficial for us to factor it this way first. So the difference of perfect squares is x cubed minus 1 times x cubed plus 1. Now I have x cubed minus 1 times x cubed plus 1. That's the difference of perfect cubes, and that's the sum of perfect cubes. So x cubed minus 1 factors into x minus 1 times x squared plus 1 times x is x plus 1 squared is 1. And then x cubed plus 1 factors into x plus 1 times x squared minus x times 1, so just x minus x plus 1. So really, we get x minus 1 times x plus 1 times x squared plus x plus 1 times x squared minus x plus 1. And if you went through and first did the difference of perfect cubes, you would get the same answer. It's just going to be a little bit trickier along the way. You might not get to the completely factored form that we got to here. Number 4, factor 128x to the fourth plus 54xy cubed. So, we have to ask ourselves, is this the difference of perfect squares? Is this the difference of perfect cubes? What's going on here? So the first thing that we always need to look for when we factor is there a GCF? Is there a GCF between 128x to the fourth and 54xy cubed? Well, they both have an x in them, so I can factor out an x. And what's the greatest common factor of 128 and 54? Well, I know they're both multiples of 2. Maybe that's not the greatest, but let's figure that out. So after I factor out 2x, I took out that GCF. What am I left with? I'm left with 64x cubed plus 27y cubed. And that looks promising. That looks promising because this is the sum of perfect cubes. This is 2x times 4x cubed plus 3y cubed. How do I factor the sum of perfect cubes? Well, that 2x is coming along for the ride. I get 4x plus 3y, and then I get the first term squared, so 16x squared, minus their product, so minus 12xy, plus the second term squared, 9y squared. And that is equivalent to our original expression here. Number 5, show that x plus 2 is not a factor of x cubed minus 8. So if x plus 2 was a factor of x cubed minus 8, I could multiply something times x plus 2 to get x cubed minus 8. So let's do x cubed minus 8 divided by x plus 2 and see what happens. Let's see, is there something times x plus 2 that gives me x cubed minus 8? I'll do the reverse tabular method. You could do long division. It's up to you. X cubed divided by x is x squared. So I'm going to have a x squared term, an x term, and a number term. I get out x cubed. I need to fill in the missing terms. 0x squared, 0x, negative 8. What times x gives me x cubed? X squared. X squared times 2 is 2x squared. I want 0x squared, so I'm going to have to put a minus 2x squared there. What times x gives me negative 2x squared? Minus 2x. I get negative 4x. I want 0x and I have negative 4x, so I'm going to need to add 4x back in. Plus 4. 4 times 2 gives me 8. But I wanted to get out negative 8, so clearly something went wrong here. We'll save that for the end of the unit of when we start getting remainders. But clearly there's nothing times x plus 2 that gives me x cubed minus 8. So because we had that remainder, it's not a factor. So we have a remainder. So x plus 2 is not a factor of x cubed minus 8. So therefore, is x plus a factor of the difference of perfect cubes? No. Only x minus a is a factor of the difference of perfect cubes. It's a factor of x cubed minus a cubed. X plus a is not a factor of the difference of perfect cubes. X plus a is a factor of the sum of perfect cubes, but not the difference. Compute the quotient, make a conjecture on how we can factor x to the fifth minus a to the fifth. So I'm going to do this doing reverse tabular. I think this is a little bit faster when you have all those missing terms than long division, but you could do this with long division. X to the fifth divided by x gives me x to the fourth. So that's x to the fourth, that's x cubed, that's x squared, that's x, and that's my number. I get out an x to the fifth from this row, from that box. That diagonal has to give me 0x to the fourth. That diagonal has to give me 0x cubed, 0x squared, plain old x, and then my number. which I know is 0x, and then my plain old number is negative 32. So we go through and do the reverse tabular method now. What times x gives me x to the fifth? X to the fourth. Multiply through. I want 0x to the fourth, so I'm going to need 2x to the fourth there. So I get 2x cubed times x gives me 2x to the fourth. I'm going to multiply through. I get negative 4x cubed, so I need 4x cubed here to add to 0x cubed. Plus 4x squared times x gives me 4x cubed. Multiply through. Negative 8x squared plus what gives me 0x squared? Well, 8x squared should go there. I get plus 8x. 8x times negative 2 is negative 16x. So I need a 16x up there. What times x gives me 16x? Well, plus 16. 16 times negative 2 is negative 32, as I want. So that quotient is x to the fourth plus 2x cubed plus 4x squared plus 8x plus 16. So how can I use this to factor x to the fifth minus a to the fifth? Well, x to the fifth minus 32 is really x to the fifth minus 2 to the fifth. So we know x minus 2 is a factor of x to the fifth minus 32. X to the fifth minus 32 can be written as x minus 2 times x to the fourth plus 2x cubed plus 4x squared plus 8x plus 16. So what if I just don't have a number there and I have x to the fifth minus a to the fifth? Well, I'm going to get a factor of x minus a. And then what's the pattern that we see here? I get x to the fourth. Well, 2 is my a, so plus ax cubed. 4 is a squared x squared. 8 is 2 cubed, so plus a cubed x plus a to the fourth. Again, that's that looking for and making use of patterns and structure of we can factor the difference of perfect fifths as this. Do you actually need to know how to do this? No, you only have to know how to memorize the sums and difference of perfect cubes. This is just taking that idea and extending it further. Compute x squared plus y squared quantity squared. Show all your work. So what does it mean to square something? It means to multiply it by itself. Hopefully you have that concept mastered now. I'll use the distributive property to multiply these two binomials. You could do it with a table. So I'm doing x squared times that quantity plus y squared times that quantity. Now I'm going to use the distributive property 2 more times. X squared times x squared is x to the fourth. X squared times y squared is just, well, x squared y squared plus x squared y squared plus y to the fourth. Who are my like terms? Well, these are both x squared y squared, so I have x to the fourth plus 2x squared y squared plus y to the fourth. Okay? Hopefully, as I said by now, you're comfortable with squaring binomials. That's a big concept that I hope you mastered. Here's a throwback to geometry. When we graph the solutions to the equation x minus 3 squared plus y plus 2 squared equals 16, we get a circle. Hopefully you recognize this equation as the equation of a circle. That was something you talked about at the end of geometry last year. What's the center and what's the radius of the circle? So the equation of a circle is x minus h squared plus y minus k squared equals r squared, where the center is hk. Remember, the center goes in as their opposites into the equation. So I have x minus 3. That means the center has an x-coordinate of positive 3 and a y-coordinate of negative 2 because they go in as their opposites. That's my center. And I have a radius of, well, that's the radius squared. I have a radius of 4. 9. Find the average rate of change of g of x over the interval from negative 2 to 4. So average rate of change, we need to use the slope formula. We need the change in y over the change in x. Those are the x values. X equals negative 2 and x equals 4. I need their y values. So let's find g of negative 2 minus g of 4. Those are the y values over negative 2 minus 4. If you switch the spots of -2 and 4, as long as you do it consistently, you'll get the same answer I do. G of -2 is 4 times -2 cubed minus 5 times -2 squared plus 3. I'm going to hop over the calculator, and I want 4 times -2, 4 times -2 cubed minus cubed, not to the 33rd, minus 5 times -2 squared plus 3. So that has a y value of -49. Let me just make sure I typed it in right. Yes, we did. So g of -2 is -49. And then I'm going to go back up and grab that, and now we're going to find g of 4. I'm going to plug in a 4. 4 times 4 cubed minus 5 times 4 squared plus 3. So I'm going to plug in I'm going to change all those -2's into 4's. You could do this by hand, but you have a calculator, so you won't make mistakes. 179. We get 179. So those are the y values of those points. So now we can compute -49 minus 179 over -6. So -49 minus 179 divided by -6 is 38. So the average rate of change is 38. The slope of the line connecting those 2 points has a slope of 38. Average rate of change is just a concept that's going to keep coming back at us, so we need to get good at doing it. Number 10, what is the difference of these two polynomials? If the difference of these two polynomials is multiplied by 1/2 x squared, what's the result written in standard form? So whenever I subtract, I distribute that -1 through. 3x squared minus 2x plus 5 minus x squared minus 3x plus 2. We'll deal with that 1/2 x squared in a minute. Let's just see what this polynomial is simplified. I have 2x squared minus 5x plus 7 after I combine like terms there. And I want to take that polynomial, and they asked us to multiply it by 1/2 x squared. What do I have to do now? I need to distribute that in. 2 times 1/2 is 1, so I get 1x to the 4th minus 5/2 x cubed plus 7/2 x squared. Nothing else we can do from there, so that's the solution. Is it written in standard form? Yes, x to the 4th, x cubed, x squared. The exponents decrease. Alrighty, that was lesson 5.